Hi, my name is Eryk Halubek, and I'm an undergraduate student at Institute of Physics, Lodz University of Technology. And today I would like to show you a short presentation that is an introduction to quantum mechanics. So if you're a physics student, this is something for you. In this presentation, I will discuss what led scientists to the theory called quantum mechanics, the necessity of the quantum wave function, which describes the nature at a very small scale. Then I will discuss short and simplified derivation, let's call it the derivation of the Schrödinger equation. It's not a derivation, but in formal sense, but there are some intuitions that you could get from what I will show you. So, what were the main factors that contributed to the, let's say, necessity of existent existence of such theory as quantum mechanics? First of all, one of them was the black body radiation problem. A black body is a body that almost absorbs all the radiation falling on it. As we can see here, it could be realized by a tiny hole in the sphere. So if a light beam falls into the sphere, then it bounces off its walls and almost dissipates all its energy. And it's very unlikely to get out of it. So we can say that with a very good approximation, such thing absorbs almost all the radiation falling on it. And we call such thing a black body. And in 80, in 1860, Gustav Kirchhoff introduced this term as an idealized physical body that absorbs all electromagnetic radiation falling on it. And this body was observed to emit a radiation which intensity depends on its temperature. And actually, we see here the equation that describes the um, wavelength at which the intensity is maximal at a certain temperature. And T is a constant, T is a temperature in kelvins. So if we increase the temperature of a black body, it's not exactly a such thing. It doesn't, in reality, in most cases, mean such thing as we can see here, as this tiny hole in the sphere. But most objects, let's say, that are not too mirror-like, that don't reflect that much of the radiation, could be pretty well approximated by a black body. And we can imagine, let's say, a sphere, a metallic sphere that we heat up to a certain temperature. And as we know, metal at a certain temperature starts glowing. So if the temperature is high enough, we can see the radiation that is emitted by this metal object. But the temperature has to be really high, like many hundreds of degrees Celsius. So if we look at this equation, we can see that the higher the temperature, the lower the wavelength would be of that radiation. And later we will see that the lower wavelength of the radiation corresponds to higher energy of the radiation. and that higher energy we can observe as visible light. What we can see is just an electromagnetic wave, but it has to be at very specific range of energy. It has to be, its energy has to be beyond certain threshold, but below the, let's say below some ceiling of the energy, some maximal level. And that we can call it visible light, this radiation. So this law that we saw corresponds to the theories that try to explain the behavior of the black body, and those classical theories led to the absurd conclusion that the total energy emitted by any black body should be infinite. It's obviously impossible. And in the year 1900, Max Planck announced a formula that fit the experimental results perfectly, which we can see here below, and solves the problem of this infinite energy. So in this equation, we can see that the intensity of electromagnetic radiation depends on the frequency. The symbol here is a Greek letter nu. Is equal to 2 times the Planck constant times the frequency squared divided by c squared, which is the speed of light. C is the speed of light in a vacuum. And here, K is a Boltzmann constant. T is temperature in kelvins. So this equation describes perfectly how is how the intensity of electromagnetic radiation emitted by a black body is distributed. Here we can see that according to this law, the curves which are 3000 kelvins, 4000 kelvins, and 5000 kelvins deviate significantly from classical theories. The classical one particular classical theory that is which from which there was this function that's presented on this graph generated, and obviously the classical theory was not right because at very small wavelengths, very small wavelengths, the intensity of light emitted should be really high, and in reality, in fact, it goes to infinity. It's impossible. And here we can see really nice smooth curves that are generated by Planck's law. But with Planck's law, there were some revolutionary statements that um, portions that there are portions of electromagnetic radiation which are called quanta, and that radiation could be also could be only emitted in such dividable portions. And Einstein used this concept, which originated from Planck's um, papers. And in 1905, he explained the photoelectric effect. So he assumed that, as opposed to the common view, which which was which originated from classical theories, that the higher the intensity of a light, the higher the energy of an electron should be. That's the electron that is ejected from a metal by electromagnetic radiation, which is not true. Einstein proposed that each portion of electromagnetic radiation, which is called a photon, could only eject one electron from the metal. And only photons with sufficient energy could do that. So if intensity is related to the amount of these photons in at a certain period of time, it wouldn't affect the kinetic energy of the electron, how how quick it is ejected from the metal, because we could imagine it, we could imagine the situation as two balls bouncing off each other and giving themselves energy. So if the intensity is high, it doesn't necessarily mean that the balls have the balls which are referred to as photons have a high energy. It only means that there are many of them. So this was the thing that also contributed to the foundations of quantum mechanics, and it was a really revolutionary view on uh, the physical phenomena. Next thing that contributed to the development of quantum mechanics was the work of Louis de Broglie. Here we can see it's him sitting next to his desk, and he, if one thing could be derived, well, yeah, derived from his work, the most important thing would be this equation that we see here, the lambda equals h divided by p, which describes the wave-like nature of particles. That particles, in certain situations, at certain conditions, could be considered and should be considered as waves. And here we could determine the wavelength of such wave that corresponds to certain particle with a momentum p. So that's how you would do that. And this was also a very revolutionary statement that like an particle, like an electron, could interfere with itself and with other electrons, causing interference patterns just like light does. So in spite of being a particle, which we imagine as a point with a certain mass and properties, it should be considered in certain situations as a wave. Okay, and then if particles are wave-like, what is the wave equation that describes these waves? Because we know that waves in very at a very simple level that we teach in high school have a wave equation, very simple wave equation that describes a two-dimensional case called a traveling wave. So we have some intuition that waves should also here have a wave equation that describes them. It's just an intuition, but it turns out to be the right one. So, what should be the characteristics of a new wave equation? It must be consistent with the broad postulate, and this postulate that the energy of photon of electromagnetic radiation quantum is expressed by this relation. So this is energy, this is Planck constant, this is the frequency of that radiation. And the frequency is divided by the energy of the photon, is described as the energy of a photon divided by Planck constant. And also, this equation, this new equation, wave equation, must be linear in wave function, meaning that any linear combination of solutions must be also a solution to the new equation. That would be nice. And for constant potential energy, this equation must have sinusoidal traveling wave solutions of constant wavelength and frequency. So we could start from these postulates. The first two are well known, as I discussed them just a few seconds ago, and here we can see the expression for total energy of a system. Here we can see that the first thing is a kinetic energy, P is a momentum, so the momentum squared divided by 2m. If you write the P, the momentum as m times tau, then you get m squared, v squared divided by 2m. So it's m times v squared divided by 2 is kinetic energy for a particle with mass m, and here is potential energy. That depends, in general case, of position and time. But here in our derivation, I also simplified it that I restricted my calculations to one-dimensional case. So that's why you see here x not r vector of that will describe where the particle is in three-dimensional space. So if we substitute certain things to get such equation, p h divided by lambda, it's substituted here. This leads to the following equation, that h time the new frequency is from here. And this equation relates to the Broglie wavelength and the energy frequency relationship. Now, using the relations for angular angular frequency and k, which is called wave number, is 2 pi divided by lambda, and h bar is a reduced Planck constant, and Planck constant divided by 2 pi. We can transform the equation from the previous slide to the following equation. So you could try to do that as an exercise. You should try to do that. And then now let's assume that wave function is of the following form, where a is constant. It may look pretty weird, but it makes some sense. You will see that that it actually makes some sense. So here we can see the e to the power of I times something, which is a general solution to many differential equations that you may have some intuition that it somehow makes sense if you think about it in such a way. This letter is psi. It's a Greek letter that we use to write the wave function, just because we like to write it as such using this letter. And the time derivative of this function is as follows. minus I times omega times psi. So minus omega comes from here, and there's I also. So right. And now knowing that E is h bar times omega, which comes from previous equations, we could write that E times psi is equal to I times h bar times the time derivative of this wave function. But it's a partial derivative, the symbol that you will see here, because in this wave function, it is a function of two variables. And now this is the first part of the Schrödinger equation that connects total energy with the time derivative, the wave function. Now let's compute the second derivative with respect to position. This is also a partial derivative. And so it would be equal to minus k squared times psi. Go ahead and try to derive it as an exercise. After then, we could substitute p squared is equal to h bar squared times k squared, where k is 2 pi divided by lambda. And after some pretty clever manipulations, you could arrive at this equation, which then you could you could connect with the, the previous part to get the Schrödinger equation. So we arrive at the Schrödinger equation. It's an equation that describes the quantum state evolution in time. Quantum state is just a system of two bodies, three bodies, like the most simple case, one electron. It could be a system of two electrons, very small bodies that interact with each other. And the wave function is the solution to this equation. And each quantum system has its own quantum wave function that holds all the information about the system. So how is it possible that such, let's say, it's quite simple function could have all the information, could hold all the information about the system, and how we could extract this information by using certain operators, like we can see here. This is an operator for total energy. So I is an imaginary unit times h bar and the time derivative, partial time derivative. So by using these operators, um, we could extract the things that we want from this wave function, which will be discussed in next lectures. And one thing that is also important to point out now is that when you have two electrons, it's not that each of these electrons has its own wave function, and you consider interaction between them as the interaction between the two wave functions. You do something like you have one wave function for the whole system. So these two electrons you should be considered as a system as a whole, and then you have um, wave function for this whole system, and then this wave function uh, would evolve according to this equation, and this evolution would describe how the system behaves. So that's it for this lecture, and see you next time.